Hello everybody. In this session we are going to discuss about design of shaft and keys. So it is unit 3 session number 4. In the previous sessions we have discussed about the basics of shafts, then some derivations on finding the diameter of shaft, and we have discussed about two problems on shafts. Today we are going to discuss about simple problems on design shaft based on the shaft subjected to twisting moment or shaft subjected to bending moment only. So as I told, the problems are based on shaft subjected to twisting moment or bending moment only. So in the previous class we have solved the problems on shaft subjected to twisting moment only. So in this session I will continue with that, and in addition to that I am going to show how to solve the problem when the shaft is subjected to bending moment only. So now let us take the third problem in the chapter number 3. Find the diameter of solid shaft to transmit 20 kilowatt at 200 rpm. The ultimate shear stress for the steel may be taken as 360 MPa and a factor of safety as 8. If a hollow shaft is to be used in place of a solid shaft, find the inside and outside diameter when the ratio of inside to outside diameter is 0.5. So this is the detail they have given. So from the first sentence, that is find the diameter of a solid shaft to transmit 20 kilowatt at 200 rpm. It means that they have given the values, that is the power value they have given and the speed they have given. By using this you can easily find out the torque transmitted by the shaft. Next is he has given the ultimate shear stress for the mild steel material. He has given that it is 360 MPa and a factor of safety is 8. So he has given the ultimate stress, but we have to calculate the working stress for mild steel shaft. So we have to calculate by using the equation. So sigma u divided by factor of safety. By doing that, you are going to calculate the working stress. And he has told that we have to calculate the diameter of a hollow shaft also. So first thing is, first we have to find out the solid shaft diameter. Then if you want to replace the solid shaft by hollow shaft, what will be the diameter, that we are going to find out. So in case of a hollow shaft, he has given the ratio of inside to outside diameter as 0.5. So these are the given details. Now we will start solving the problem. So this is the given data. As I told, N is equal to 200 rpm, P is equal to 20 kilowatt, factor of safety is 8, ratio of diameters di by d naught is equal to 0.5, ultimate shear stress 360 MPa. So these are the given details. Now what is working stress, that we are going to see now. See, as I told, the working stress is the stress induced while the shaft is transmitting a torque. For example, as you know the stress strain diagram, so ultimate stress is that point where it is going to break. So you cannot consider the ultimate stress for designing a shaft. We have to consider the working stress. So usually the working stress for mild steel shaft is 41 Newton per millimeter square if it is a mild steel shaft. It means that it is within the elastic limit. If you assume a sigma u, that is ultimate stress, if you assume, so it will be in a plastic zone, so there will be more chances of failure over here if you use the ultimate stress for the calculation. That's why we are going to use the working stresses. So now what I am going to do is I am going to divide the ultimate stress by a factor of safety that will give you the working stress. That is, working shear stress is given by tau is equal to tau u divided by FOS, that is factor of safety. So that is nothing but 360 divided by 8. This will give rise to 45 Newton per millimeter square. So this is the working stress. So once you find the working stress, next thing is to transmit next thing is to find out the torque transmission capacity of the shaft. And we know the equation T is equal to 9.55 into 10 raised to 6 into P divided by N. So by using this equation, we can easily find out the torque transmission capacity of the shaft. And this equation is available in your design data handbook, page number 50, 3.3a, equation number 3.3a. So if you substitute the value of power, so you have to substitute the value of power in kilowatts and N in RPM. If you do that, you are going to get the answer as T is equal to 955 into 10 raised to 3 Newton millimeter. This is the answer you are going to get. Further, if you want to find out the diameter of a solid shaft, so we have an equation D is equal to 16T divided by pi into tau whole raised to 1 by 3. So this is available in your design data handbook, equation number 3.1, page number 50. So by referring your design data handbook, you can write the equation. Again, if you substitute the value of torque and if you substitute the shear strength of the, that is working shear strength of the material, so then you are going to get the diameter as 47.6 millimeter. As we know, this is not the standard diameter. We have to find out the standard diameter. Again, from design data handbook, page number 57, we can easily find out the standard diameter, that is by referring the table 3.5a, page number 57. So the next standard diameter is D is equal to 50. That is selected for the torque transmission. So the next in the next slide, I am going to explain how to find out if you are using the hollow shaft instead of a solid shaft, then what is the formula to find out the diameter of a hollow shaft, that we will see. So till here it is same. You have to find out the working stress, then you have to find out the torque transmission capacity of the shaft. Only thing is, instead of a diameter of a solid shaft, we have to write the diameter. We have to find the diameter of a hollow shaft. So the formula is 16T divided by pi into tau 1 by 1 minus k raised to 4 whole raised to 1 by 3. So that extra term 1 by 1 minus k raised to 4 we have to include for hollow shaft. Again, all of you know k value is nothing but it is the ratio of diameter. So in this problem, he has given the ratio of diameters, that is di by d naught is equal to 0.5. So we are going to substitute that value inside the equation 3.1. So this equation is available in your design data handbook. Now I am going to substitute the value of t and tau. And again the k value, that is 0.5, I am going to substitute in this equation. So we are going to get the value as 48.6 millimeter. Again, you can notice this diameter is greater than the previous diameter. So again, it is not the standard one. We have to refer the design data handbook and we have to write the standard diameter. So it is available in page number 57, table number 3.5 of DDHP. Standard diameter of the shaft corresponding to the 48.6 millimeter is 50 millimeter. Hence, outside diameter of the hollow shaft is D naught is equal to 50 millimeter. Once if you know the outer diameter of the hollow shaft, you can easily find out the inner diameter of a hollow shaft by using the equation, that is di is equal to d naught into k is equal to 50 into 0.5 is equal to 25 millimeter. So this way you can easily find out the diameter of a hollow shaft. ಎಲ್ಲರಿಗೂ ಗೊತ್ತಾಗಿದೆ ಅಂತ ಅಂದ್ಕೊಂಡಿದ್ದೀನಿ. ಡಯಾಮೀಟರ್ ಆಫ್ ದಿ ಸಾಲಿಡ್ ಶಾಫ್ಟ್ ಮತ್ತೆ ಡಯಾಮೀಟರ್ ಆಫ್ ದಿ ಹಾಲೋ ಶಾಫ್ಟ್ಗೆ ಒಂದೇ ಡಿಫರೆನ್ಸ್, ಎರಡು ಈಕ್ವೇಶನ್ಸು ಒಂದೇನೆ. ಬಟ್ ಇದರಲ್ಲಿ ಏನಾಗುತ್ತೆ, 1 by 1 minus k raised to 4 ಈ ಎಕ್ಸ್ಟ್ರಾ ಟರ್ಮ್ ಏನಿದೆ ಇದನ್ನ ನೀವು ಸೇರಿಸ್ಕೋಬೇಕಾಗತ್ತೆ. ಸೊ ಇಫ್ ಯು ಡೂ ದಟ್, ಅಪಾರ್ಟ್ ಫ್ರಮ್ ದಿಸ್ ಇದನ್ನ ಬಿಟ್ಬಿಟ್ರೆ 1 by 1 minus k raised to 4 ಬಿಟ್ಬಿಟ್ರೆ ಇನ್ನು ಉಳಿದಂಗೆ ಎಲ್ಲ ಪ್ರೊಸೀಜರು ಸೇಮ್ ಇರುತ್ತೆ. ಇನ್ನೊಂದು ನೋಟಿಸ್ ಮಾಡಬೇಕು ನೀವು, ಸಾಲಿಡ್ ಶಾಫ್ಟ್ ಮತ್ತು ಹಾಲೋ ಶಾಫ್ಟ್ ಎರಡನ್ನೂ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ಕೊಂಡು ಡಯಾಮೀಟರ್ ನೋಡ್ಕೊಳ್ಳಿ. ದೆರ್ ವಿಲ್ ಬಿ ಎ ಸ್ಮಾಲ್ ವೇರಿಯೇಷನ್. ಸೊ ವೇರಿಯೇಷನ್ ಹೇಗಿರುತ್ತೆ ಅಂದರೆ, ಹಾಲೋ ಶಾಫ್ಟ್ ಯಾವಾಗಲೂ ಡಯಾಮೀಟರ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ ಸಾಲಿಡ್ ಶಾಫ್ಟ್ಗೆ. ಸೇಮ್ ಟಾರ್ಕ್ ಟ್ರಾನ್ಸ್ಮಿಷನ್ ಕೆಪಾಸಿಟಿ ತಗೊಂಡ್ರೆ ಹಾಲೋ ಶಾಫ್ಟ್ ಡಯಾಮೀಟರ್ ಯಾವಾಗಲೂ ಜಾಸ್ತಿ ಇರುತ್ತೆ. ಬಟ್ ವೆಯ್ಟ್ ಎಲ್ಲ ತಗೋಬಿಟ್ರೆ ನೀವು ವೆಯ್ಟ್ ಕಂಪ್ಯಾರಿಸನ್ ಮಾಡಿದರೆ ಹಾಲೋ ಶಾಫ್ಟ್ ಈಸ್ lighter compared to the solid shaft. ಇದನ್ನು ನೀವು ನೆನಪಲ್ಲಿ ಇಟ್ಕೋಬೇಕು. Next we will move on to the next problem. That is problem number 4. A pair of wheels of a railway wagon carries a load of 50 kN on each axle box, acting at a distance of 100 mm outside the wheelbase. The gauge of the rails is 1.4 meter. Find the diameter of the axle between the wheels if the stress is not to exceed 100 MPa. So this is the case of pure bending, and here we are going to neglect the torsion. Only we are going to consider the bending moment. That is it is the case of shaft subjected to bending only. First we are going to understand the problem. So it is a axle, railway wagon axle problem, and all of you know the different types of gauge lengths in the railway axles. So we have a narrow gauge, then we have a meter gauge. Now we are having a broad gauge. So if it is a narrow gauge, it is less than 1 millimeter, the distance between the two rails, that is known as gauge, and the gauge will be less than 1 meter for the narrow gauge. For a broad gauge, it is equal to 1 meter, and if it is for a meter gauge, it is equal to 1 meter, and for a broad gauge, usually it is 1.4 meters. So it is a broad gauge. We have to consider the broad gauge, and it is going to carry the 50 kilonewton on each side. Okay, and it is having a distance of 100 millimeter from the wheelbase. Both the sides we will have a 100 millimeter wheelbase, that you can see here. This is a sketch. So here you can easily notice this is the railway wheels, okay, wagon wheels, and this is the extended part, and it is 100 millimeter from the wheelbase. This is the wheelbase. C and D are the wheelbases. A and B are these are the loading points, and in each side it is 50 kilonewton. Load is equal to 15 kilonewtons. And here in this problem you can clearly notice they have given the bending stress. They have not given the shear stress. This is the bending stress. That's why I have written as sigma B is equal to 100 MPa. So here the shear stress is not given. It is bending stress. They have given the bending stress, because in this problem we are going to neglect the torque transmission capacity. Okay. So I have listed the given data. As I told, it is equal to 15 kilonewton. Load on each side is 50 kilonewton, and the length of the axle is 1.4, that is from one wheel to another wheel, that is 1.4, and the extended length is 100 millimeter. On each side there will be extension of 100 millimeter, and they have given the sigma B value. They have given it is 100 MPa. So they have given in terms of MPa, that you have to write it in 100 Newton per millimeter square. So by using this, first we have to calculate the maximum bending moment, then we have to calculate the diameter of the shaft that can withstand the bending moment. Okay, so this is the one, this is the setup, and you can easily see the bending moment. The maximum bending moment will be at the sides. Okay, the extended sides. On both sides it is 50 kilonewton. So you will get the maximum bending moment at C and D. So that's why what I am going to do is I am going to write, that is load into distance. Load is 50 kilonewton and the distance is 100 millimeter. So you are going to get the 5 into 10 raised to 6 Newton millimeter as the bending maximum bending moment. So and it is acting at point C and D. Once if you know the maximum bending moment, you can easily find out the diameter. So the diameter is given by D is equal to 32 m divided by pi into sigma B whole raised to 1 by 3. Again, this equation is available in your design data handbook, page number 50. Okay, this you can refer and write. Now what I am going to do is I am going to substitute the value of m and sigma b. As I told, the sigma b value is 100 MPa, that is equal to 100 Newton per millimeter square, and m is 5 into 10 raised to 6 Newton millimeter. By doing the substitution, you are going to get the answer as 79.8 millimeter. Again, this is not the standard diameter. We have to refer the table 3.5. So page number 57 of DDHB. By doing that, we are going to select the standard diameter. And here the standard diameter is that is standard diameter of the shaft corresponding to 79.8 millimeter is 80 millimeter. Hence, D is equal to 80 millimeter is selected. And this diameter, if you use this diameter, it will withstand the bending moment of 5 into 10 raised to 6 Newton millimeter. So that you have to remember. So this is the case of pure bending, and in this problem we have neglected the torsion. Only we have considered the bending moment. In this session we have learned that how to calculate the working stresses when ultimate stresses are given, and we have calculated the diameter of a solid as well as a hollow shaft subjected to twisting moment or bending moment only. So we have solved two problems in this session. In the first problem, we have learned that how to calculate the diameter of a hollow shaft and a solid shaft subjected to twisting moment only. And in the second problem, we have studied about the shaft diameter, how to find out the diameter of the shaft subjected to bending moment only. Thank you. Next is, I am going to ask some MCQs on session number 4. First MCQ is, what is the working shear stress of mild steel having the ultimate shear stress of 360 MPa? Assume factor of safety as 8. Answers are 42 Newton per mm square, 45 Newton millimeter, 45 Newton per mm square, 45 Newton millimeter. Please give your answer. The right answer is 45 Newton per millimeter square. So here he has given the ultimate stress. We have to find out the working stress by using the factor of safety. That is 360 divided by 8 we have to do. If you do that, you are going to get the answer as 45 Newton per millimeter square. Next MCQ is, what is the inside diameter of the hollow shaft if the outside diameter is 50 millimeter? If K is equal to 0.5. Answers are 75 millimeter, 25 millimeter, 30 millimeter, none of this. Please give your answer. The right answer is 25 millimeter. Next MCQ is, bending stress is dash than the shear stress of the material. Answers are equal, more, less, none of this. Please give your answer. The right answer is more than the shear stress of a material. So if you take a mild steel shaft, it is having a shear stress of 41 Newton per millimeter square, whereas the bending stress has 83 Newton per millimeter square. Next MCQ is, maximum permissible bending stress for mild steel shaft without keyway is. Answers are 41 Newton per mm square, 56 Newton per mm square, 100 Newton per mm square, 83 Newton per mm square. Please give your answer. The right answer is 100 Newton per mm square. So if it is a keyway shaft, then it is 83 Newton per mm square. So if it is a without keyway shaft, it is 100 to 110 Newton per mm square. So the right answer is 100 Newton per millimeter square. Next question is, bending moment is given by. Answers are force into distance, force divided by distance, force plus distance, force into RPM. Please give your answer. The right answer is force into distance. Next MCQ is unit of bending moment is, answers are Newton millimeter, kilonewton millimeter, Newton meter. Please give your answer. The right answer is all of this. So we can use Newton millimeter, kilonewton meter or Newton meter for as a unit for bending moment. Next is 1 MPa is equal to, answers are 1 Newton millimeters, 10 raised to 3 Newton per millimeter square, 1 Newton per millimeter square, 10 raised to 6 Newton per mm square. Please give your answer. The right answer is 1 Newton per millimeter square. Next MCQ is revolution of the shaft is measured by RPS, that is revolution per second, B revolution per minute, that is RPM, radians per second, or all of this. Please give your answer. The right answer is all of this. Thank you.